Alright, so I call this video "What the heck are revolved solids?" because some students are just really confused by the whole concept of solids of revolution. So in this video I'm not going to talk about what disk method is or what washer method is or shells. I'm just going to talk about three-dimensionally what these things represent, because I know that's a real hang-up for students who like to see things visually. But if you just want to get right into plugging and chugging and see how to do those integrals, then you can always skip this video. It's not very long anyway, but you can skip it and move on. Alright, revolved solids. What the heck are they? Well, basically we're looking at things that are made by spinning other things. So the most straightforward comparison would be if you look at a potter's wheel. Like, let's say that you're making something out of clay, so you throw the chunk of clay down there on the spinning wheel and you kind of use your hands to mold it into a shape. Any shape that can be made on the potter's wheel can be made by revolving something, a cross section. So these dashed lines right here, what that's representing is the spin axis. So that would be like the center of the potter's wheel. So let's say we had a potter's wheel and we just threw down, there, oops, it's kind of crooked. There's the potter's wheel. And we just throw a clump of clay on there and we start working it, and a couple of minutes later we've got a bowl shape. So we've got a shape like this. It's a cross section. Of course it's a bowl, so it actually, I just sort of cut it in half to reveal its shape. But we've got a bowl shape, so it's kind of like this, whatever. But as you can see, if I wanted to sort of tell you what that bowl looked like, I could just say, you know what, it has an axis down the center, because anything round, you can sort of describe it as having an axis. In Algebra 2 you talk about axis of symmetry, or whatever. So there's the spin axis, that's sort of the center line. So if you look at a top view of this same bowl, it's a bad circle, top view of the same bowl, that spin axis is right down the center. So no matter what, it's just at the center of the circle. It's right down the roundness. And if you cut this bowl across any plane, it's always going to be a circle or a donut or something. So that's what a revolved solid is. It's something round, and we get it by sweeping out shapes. So just like if you had a shape, you could describe it as having been something revolved, like this U shape revolved would give you a bowl. You could look at it the other way and say, hey, what happens if I take something like this rectangle and just spin it and see what it looks like? Well, I would end up with this disk thing over here. So if I kind of like if I sort of put on my X-ray vision, it's like you can sort of imagine there's a rectangle right there. Any place you cut this thing, you're going to end up with a rectangle cross section. You'll notice I'm only drawing rectangles that don't go all the way across, they only go halfway across from the spin axis to the edge. But these rectangles don't go all the way across, because then that would be a diameter, not a radius. So if I take this rectangle and spin it, that's the axis of symmetry, which means I'm going to end up with a matching half that shoots off to the left here. Similarly, let's take this circle right here and spin it. Now if we take this circle and spin it around an axis right down the center, we'll just end up with a sphere right where we're looking at it. So we'll just end up with a sphere that's the same size as the circle. But if I spin it around the spin axis right here, I'll end up with this, I think it's called a toroid. But over here, it's like there's one circle. So the cross section of this nub on the right is a circle. But then again, the cross section of this thing over here is also a circle. It's really hard to draw this. There's a circle if you cut it and cross over here. So no matter where you cut it, you're going to end up with the same shape that created it, this circle. Just like no matter where you cut this disk, you're going to end up with rectangles that are the shape that created it by spinning around the axis. Alright, here's a wackier shape. As you can see, I went nuts on Illustrator to try and show what a weird shape this would be, but imagine this was like y equals x squared, just a parabola. And then this top thing is just a line like y equals x, and this point is maybe 1 comma 1. But in these problems, they'll give you a region like this, and they'll say, hey, revolve the region given, so between x squared and y equals x, take this region right here and find the volume of the solid you would get if you revolved that region around some axis. And then like right now I'm just going to say, hey, let's spin it around this axis, the y-axis. So what it's going to do is this, you can see if you stuck this thing onto a record player with this little tip right at the center of the record player, this isn't really moving. That's this point right here. It's just staying fixed. It's the very bottom crevasse of the bowl. And then this face, this line right here is going to create the inside face of the bowl. So that's this outside corner as it goes around a giant circle. You know, here's one of my representative cross sections. So again, just like with the disc, anywhere I look, I can draw one of my representative cross sections in here. So you can see that if you cut this bowl with a saw or something, no matter where you cut it, you're going to get a flat top surface with these sort of curved bottom surfaces. And they're all identical to this shape. So if we colored them in, we should get, now this is in perspective, so that's why they're all kind of a little bit different shape. But the point is they'll all be the same shape. If we had the actual three-dimensional thing in front of us and we cut it up, they'd all be the same shape as this region. And of course, so it's because the top of the top, which would be the inside of the bowl, this is a flat line that we spun, so that's why we ended up with flat inner surfaces, kind of a cone shape inside of the bowl. And then the outside of the bowl is curved, because we had a curve. You know, this parabola is a pretty curvy shape. So as that was spun around, that sort of swept out this curvy outside of the bowl. Here's a shape we're going to see a lot of, and this is where a spin axis really matters. So here I just took this an upside down parabola, you know, centered right there. That's its vertex. And then I spun it around two different axes. So first I spun it around this axis. And you can see that because the region, the axis actually touches the region right here, like it's right in the next to each other. What we got was a bundt cake with no hole in the middle. If you looked at a top view of this thing, there is no hole down the middle. Whereas down here, because the closest the region ever gets to the spin axis, there's this separation here of empty space. This is going to form a gap. And that's why there's a big gap here between, if the spin axis is like right here, there's this gap, this hole, because as we swept this out, this ends up forming the corner of a hole, or the edge of a hole. And then of course this outside thing, that forms the outside corner. So this outside corner was all formed by this corner. The inside edge was all formed by this little tip that's closest to the spin axis. And then of course this is sort of the crest here of the bundt cake. I call this a bundt cake. I don't know what you call it. I don't know if everyone calls it a bundt cake or just where I'm from in the Midwest, but the point is that no matter where you cut this cake thing or donut thing in half, no matter where you cut it, you're going to end up with cross sections that look like this. So that's the whole point of revolved solid. And like I said, moving the axis can do a lot of things. So if you look at these top two, this time we're looking at a very similar shape. It's just half a circle. So it's basic. So this first one is really just a donut with barely any hole in the middle, or a bagel with almost no hole in the middle. And because it has a flat bottom, so if we were to flip this thing over, it's got a totally flat bottom because the shape that we spun around had a flat bottom. If I want to make a whole donut that's round like a normal donut or bagel, I'd have to have had the bottom half on it as well. Don't have the bottom half, so it's just the top half of the flat bottom. But the point is that because the spin axis is right next to the region, there's no gap in there, there's no hole. Whereas if you look at this one right here, we've got a nice little gap between the spin axis and the edge of the region. So that's why I end up with a hole in the middle. So this is like, again, it's got a flat bottom, but this is like a donut that has a gap in the middle, or a hole in the middle. So both these cases and everything we've looked at so far, we always had vertical spin axes. The spin axis was always the y-axis or something. So that's what we say is a vertical spin axis. And I kind of did that because we started with a potter's wheel analogy. But what happens if you look at a horizontal spin axis? So what happens if you take this half circle and spin it around an axis that's right on its bottom edge? Well, then it's just going to sort of mirror across, and you'll end up with a sphere. So if you take half a circle and spin it around its flat edge, you're going to get a perfect ball. But then that same shape, the same half circle spun around with a gap, and now you got a hole in the middle just like always, except on these other ones, the hole in the middle is just a different shape. We had kind of a curve coming into the hole, whereas on this one we have a long sort of bore. It's almost like we drilled a hole through it because this is all flat. So if you take this flat thing and spun it around this axis, you end up with a cylindrical hole down the middle. Because the distance from the spin axis to this edge is constant, this gap and this gap and this gap and this gap, that's all constant. That means the hole in the center of the shape we end up with is a constant cylinder. And then if you really want to get crazy, if instead of spinning around this axis, we'd spun the same half circle around this axis, then what happens? Then we would have gotten, the inside of the hole would have been kind of a shape like this. It's really hard to draw, but then the inside of the hole would be more like a shape like the inside of a donut, where it's curved, but the outside, this hard edge, this flat edge, would form the outside. So that would have made this whole thing have sort of a flat exterior like a tire, but then have a really curvy inside. Same thing at the bottom, it would have been flat like this with curved inside. So, hope that makes sense. Point is, when you spin something, the shape of the region and the position of the spin axis really makes a big difference in the shape you're going to get. But don't worry, we'll get tons of practice with this and all the hours and hours of videos after this about, on the website about the washer method and shell method and stuff. I just wanted to kind of, for some people who seem to really be confused by the concept of a revolved solid, I sort of wanted to outline what the heck these things are and how they work.